everyone. Welcome to another episode of the Northeastern Large Language Model Seminar, System Seminar. Today, it's my pleasure to have Hao Lin from Infinigence AI to give us a guest lecture. Hao, a very brief bio of Hao. Hao is the chief researcher at Infinigence AI, where he works on large-scale AI training and reinforcement learning. He had this broad expertise, ranging from collective communication to the co-design of the systems and algorithm, and also to the co-optimizing computation and also communication, all in large-scale AI systems. And he's the core developer and maintainer for the system we're going to see today. I guess it's called RLinf. This is a system that is right now a leading open source reinforcement learning framework for embodied and agentic AI. With that, I guess Hao, what's yours?
Oh, okay. So hi everyone. Thank you, Professor Tan, for this kind introduction and this opportunity to introduce our work, RLinf, a flexible and efficient large-scale reinforcement learning system that is recently open source. So as a new member, we have a lot of news and features that we want to share with the community. I hope you all find them beneficial and most importantly, interesting. So, okay, I'll get started. So before we begin, let me get you some background. The background is simple. We believe we are now at the time of reinforcement learning. Today, a lot of state-of-the-art models like O1 and DeepSeek R1 use RL to further increase model intelligence. Recent paper from the DeepSeek team also shows that language models can be incentivized through pure reinforcement learning without human annotation. All these exciting breakthroughs in RL has demonstrated that scaling RL computation is a pressing demand of our next step towards AGI. However, scaling RL faces the challenges of workflow diversity. With the rising of agentic and embodied AI, RL workflows have also diversified. With embodied AI, RL interacting with simulator or physical world, and the agentic RL interacting with various tools. And apart from diverse scenarios, different algorithms also introduce very different workflows, and we are having more algorithms every day. Another major challenge is component heterogeneity. For traditional LLM components, we already have generation inference, which is basically preview-only generation, and training, where generation shows high dynamicity in the response length and time, causing long tail delay on a few very long texts. In comparison, LLM training is more predictable, but consumes more accelerator resources like GPU SMs and memory. And the more heterogeneous workloads come from embodied and agentic scenarios. In embodied RL, we have simulators which mostly use GPUs to do 3D rendering rather than tensor operations. Unlike LLMs, this consumes much less GPU memory and can scale better on unlimited GPU resources. We can see that the increase of simulator environment does not lead to a linear increase in computation time. And beyond simulation, we also need to deal with physical robots, which have real-time control constraints, whose controller program needs to be run on a real-time kernel, like a Linux kernel with the real-time patch, and thus is not compatible with existing accelerators like GPUs. And further, we have AI agents using web search, coding, database, apps, MCP clouds, etc., all with highly different workloads. So consequently, we find that current RL training systems are simply not flexible enough to support the diverse workflows and components. State-of-the-art systems like a VERL, Slime, and Roll adopt the collocated mode. That is to let components share accelerator resources. This reduces per component time, but suffers from resource underutilization during long-tail generation and high overhead when switching between components. Other systems like Aerial and Async Flow adopt the disaggregated mode, which mitigates the long-tail issue, but requires more resources and causes resource idling if without async algorithms. So to efficiently scaling RL in diverse modern RL scenarios, our design philosophy is therefore to see flexibility as the key to efficiency. By maximizing flexibility, we simultaneously increase the scheduling and optimization space that are not available to rigid execution modes, and can offer quicker adaptation to new scenarios, new algorithms, and new workloads. However, a commonly accepted view in system design is that with flexibility comes complexity. Users may be given too many knobs to control and configure the system, leading to even worse performance if not properly configured. So another challenge here is that how to balance system flexibility and complexity. To achieve this, we introduce macro to micro flow transformation, or M2 flow, a novel RL system design and programming paradigm. M2 flow decouples the workflow programming and the complex optimization to resolve the tension between flexibility and the complexity, much like program compilation. It offers an easy-to-program macro workflow interface, which is broken down and recomposed into an optimized micro execution flow before or during execution. So built-in Adobe M2 Flow, we present RLinf, a highly flexible and scalable RL training framework. RLinf incorporates two mechanisms, elastic pipelining and auto context switching, to realize M2 flow transformation, and a profiling guided scheduling policy for execution planning. Also, we offer adaptive communication facility for efficient interactions among components. To obtain these powerful capabilities, all you need to do is inheriting our worker class in your RL component. And we have fully open source RLinf on GitHub and provide out-of-box support for a rich set of RL workflows, models, and algorithms to accelerate RL algorithm development and research. You are welcome to try it out. So next, I'm going to go deeper into the design of RLinf. So first, I want to show you how easy it is to construct a macro workflow in RLinf. Below is the workflow of a GRPO-based reasoning RL. The above is the corresponding workflow in RLinf. I have to use a lot of enters here to fit the code in this page, but it's really a 7-line function. As you can see, we use a data channel primitive to express the data flow, where the input data is put into a data channel and passed to the rollout. And the rollout's generation results are then put into the rollout channel, which is in turn passed to the inference component, and so on to the actor training component. In this workflow, we also provide a collective management knob of component process called worker group and a synchronization weight primitive. We will talk more about them later. So similarly, an embodied RL workflow with circular flow dependency is expressed as this, all within 10 lines of code. So this imperative interface clearly depicts the data and control flows, and thus is easy to maintain and debug. So what are these groups and channels, and how do we get them, and what can they do? I'll next show you this. So the core abstraction RLinf provides for constructing the previous RL workflows are these two, worker and worker group. A worker represents an RL component where its main logic is implemented. A typical worker main logic is shown here, the rollout worker, for generating responses based on prompts. So basically, the program logic includes three steps. First is to get the input data from the input channel, and then operate on the data, and finally put the output data in the output channel. So in fact, we find that almost all components can be clearly modeled in this I/O pattern. And by inheriting the worker class, your component automatically becomes distributed. By calling the create group and launch APIs of the worker, multiple worker processes are launched on the cluster nodes based on the placement strategy. A placement here tells on which GPUs of which node should a worker process be launched, and the worker group handle is returned to collectively manages all or a selective set of processes. For example, a worker group directly assumes all the public functions of a worker, in this case, the generate function. By calling the group's generate function, the group will dispatch and the function will be dispatched and executed on all the worker processes remotely in an SPMD manner. The function call is asynchronous and returns a handle that can be waited to synchronize the main process with the worker process, and retrieve the function's return value in the form of a list of return values from each worker process. Although I didn't show how to generate the placement because this can be done automatically by the scheduling policy introduced later, RLinf supports very flexible placement of worker process on any accelerators of any node across cluster. If you want to manually place the worker, you can use a variety of built-in placement strategies to construct the placement. Notably, the accelerators in a cluster can also be heterogeneous, mixing GPUs and NPUs and others, or no accelerator at all with only CPU in some agentic and embodied scenarios, such as a robot controller. This offers maximum flexibility at the core system level. So with this workflow, how does RLinf achieve fine-grained scheduling without changing the workflow code? We introduced two mechanisms, auto-context switch and elastic pipelining, which allow us to do temporal multiplexing of accelerators and fine-grained spatial scheduling with varying data granularity, as well as hybrid scheduling that arbitrarily combine these two strategies. So first, auto-context switching. When workers are running on the same accelerators, it's necessary to manage the accelerator resources when components switch. For example, after generation, the LLM serving engines like SGLang and VLM need to offload their GPU states to CPU to free up the memory for training. However, when the workers are not sharing devices, this operation is not needed. Otherwise, unnecessary switching overhead will occur. To unify these cases, we introduce a distributed lock primitive for acquiring and releasing accelerators. In RLinf, workers using accelerators should implement their onload and offload interfaces, which manages device resource acquiring and releasing. And when the lock detects sharing workers, it triggers unload and offload automatically. Otherwise, it does not. Different from common lock like mutex that can be contended, our device lock is a priority lock, which assigns priority to workers based on the data flow direction of the associated channel. That is, downstream workers cannot acquire locks unless upstream has acquired, put data, and release the lock to avoid deadlocks. So second, elastic pipelining. The idea of elastic pipelining is to control pipelining granularity by controlling data granularity, which is natural under our flow-like interface, and the support of running on varying data batch size of common RL components like SGLong and VLM rollout, and Megatron FSDP training with micro-batch pipelining. As shown here, we can put a full batch in the channel to completely disable pipelining, or at the global batch or micro batch level to achieve different pipelining granularity without changing the code, but only the data size. Different pipelining granularity is needed given both the performance factor and the performance factor of accelerator utilization and pipeline bubbles, as well as semantic factor like batch-wise normalization in certain algorithms. With the scheduling space enabled by M2 flow transformation, RLinf is further equipped with a profiling-guided scheduling policy to find the optimal execution plan. The policy scheduling policy is like a search-based with profiling data to facilitate our search. So with the scheduling space enabled by the M2 flow transformation, RLinf is further equipped with a profiling guided scheduling policy to find the optimal execution plan. The policy segregates the workflow graphs into subgraphs and traverse them to obtain each subgraph's plan. For each subgraph, it compares the temporal and the spatial scheduling time based on our performance model using the build using the component profiling. So this is really the complex part, but I'm going to leave this out so we don't take too much time into this. And finally, it combines the best policy of each subgraph recursively to obtain the final plan. So in general, this is our how our scheduling policy works for now. So all the above flexibility is supported by the adaptive communication facility. This includes adaptive zero-copy CUDA IPC and accelerator CCL-based communications like NICO, and the data channel introduced before, which is also equipped with a load balancing capability to ensure fair serving of consumers if requested. And most importantly, the communication between arbitrary workers can be directly achieved via a simple send and receive primitive, without the complex connection management like in Torch distributed. So all workers inheriting from the worker class can immediately communicate with each other, no matter where they are and what they are. So putting everything together, we get RLinf, a simple to use RL training framework with the a special M2 flow paradigm enabled by the worker abstraction. We evaluate RLinf on a variety of RL scenarios, models, algorithms, and scales. The result shows that RLinf consistently outperforms state-of-the-art RL system by 1.1 times to 2.13 times in end-to-end throughput. Also, models trained with RL also shows SOTA performance in both the reasoning case and the embodied case with different models, algorithms, and simulators. And this concludes my talk. I hope you find RLinf interesting. If so, we welcome you to try it out, put some issues, and better yet, pull requests. But most importantly, don't forget to give us a star. Thank you.
Let's thank the speaker.